Well, I'm going to briefly talk about smart manufacturing or manufacturing 4.0 or 4.x, which is sort of a transformation or a branch from Industry 4.0. Again, I'm sure you have heard about it. And then I'm going to present a case study which I've been involved myself, and that's the Sawmill of Future or Sawmill 4.0 or 4.x or a smart sawmill, different names and terminologies, which I'll go over that briefly as well. So here is our lecture overview, briefly talking about what is smart manufacturing or Industry 4.0, when it started, how it started, and what are the key challenges. And then I'll talk briefly about the term which started in about 2000 prior to Industry 4.0, which is called MOM or Manufacturing Operation Management, and the start of digitalization, which is the main drive of manufacturing 4.x. And lastly, as I said, I'll talk about the case study, smart sawmills. So you see how this industry is transforming to manufacturing 4.x. It gives you a good idea what do we mean exactly when we say a company, a traditional company, something like a sawmill, which they have been like for many years, they had their traditional way of doing things, moved from manufacturing 3.0, which is the automation, to industry or manufacturing 4.0. So many companies, many factories, manufacturing companies have been going through the digital transformation, which again is known as Industry 4.0. And the question is, what is it, when it happened, how it happened? But in the first place, why it happened? There are many reasons. Of course, technology, advancement in technology is the main drives, but why it happened? We can mention market pressure and the growth process, a high demand for flexibility, high quality, and fast production, and also the need for being more efficient, in particular having a smaller lot size, meaning rather than producing a lot of parts or a lot of components and having a large inventory waiting for the customers to order, how can we produce based on demand? And it means having a smaller lot size and all the logistic around that. And most often, industries from small factories to larger companies or manufacturing companies, they ask, how does Industry 4.0 apply to us? Or how can we start? So something that I call the alphabet soup of solutions is unfortunately what most of companies they hear from the books or from the like online searching or when they talk to a consultant, and they throw a lot of abbreviation like APS, use PPC or MES or ML and ERP, and I don't know most of them myself, but AI perhaps and ML machine learning are the most common that we've heard a lot. And it creates a lot of confusion actually. And this is a picture I adopted from a good textbook, Smart Manufacturing by Renee Wolf. I recommend that maybe after this course. It's a good reading and it also provides a good case study. But this sort of image, you see them perhaps here or there, or maybe a combination of that, also create, they are fancy, but they create some confusion because they are very general. For example, take a look at the image on the left, like design anywhere, build everywhere. What does it actually mean, or how does it apply to me? Or additive manufacturing, the touchless factory, smart product, connection, connectivity, and many of these terminologies again, which is they are not specific. Everybody have heard AI, for example, but how does it work actually for a particular manufacturing company? And again, keep in mind here in this content and in today's lecture, we're focusing on manufacturing actually. And beside that, there are many factors that complicate this digital transformation or this industry 4.0. First is the pace of innovation. It's overwhelmingly rapid, and there are a lot of overlap and redundancy, and and actually it creates this question that what is essential, what is optional, how or where should I start? The second challenge is many manufacturing companies have a legacy system or something I call it a tribal knowledge, meaning that they have their in-home growth or in-home solution for many things, and they are the owner of that solution or the way they manufacture something, which is functional. It works very well, but it's difficult to change it, and they sometimes resist to change it. And there is also the challenge or the issue that what if some of these experts or personnel who have this expertise leave the company? Then the company would leave with like nothing to continue on that. And lastly, the knowledge gap or a good guidance for this digitalization, and in particularly connecting a digital tool or let's say a technique. Let's talk about, for example, machine learning or maybe advanced automation or monitoring. Then is it something that aligns with the particular manufacturing goals is missing that gap, and it makes it a little bit more challenging. So as I said, let's roll back, go to early 2000 when a term coined known as MOM or manufacturing operation management. This is when, of course, there were like advanced computers became more popular, internet became popular, and it became actually the start or the core of this digital manufacturing or industry 4.0. And there are four pillars of MOM. There are many actually, but the base one are these four: MES, APS, QMS, and MI or manufacturing intelligence. Again, another alphabet soup of abbreviations. But I'm going to briefly explain each of them so you have an idea. And of course, you can read more about them, but at least you know what they are and what they do and why they are the four pillars of MOM. So MES or manufacturing execution systems, it focus on quality and efficiency. It try to see and or oversee the connection between the factories, the vendors, and the business. And it provides a real-time control and visibility and connection for the entire enterprise or the manufacturing company. APS, the advanced planning and scheduling, as the name implies, it's focus on scheduling. But what sort of scheduling? The balance between demand and the capacity a manufacturing system has. Try to optimize the logistic again and scheduling. If you recall from previous lectures, we talked a lot about optimization of like the logistic and transportation. So it deals with that. It tried to reduce the lead times, and also it focused on how quickly we can respond to change in technology or change in customer demands. Of course, and there are with APS system, there are benefits that you can scale it as the manufacturing company becomes larger, and also it's compatible with future trends and technology. QMS quality management system, as the name clearly says, it deals with quality, how to monitor and documents the quality, and it makes sure that a product follows the standard, the tolerance, and also provides a systematic way by collecting data to see if there is any trends in the quality of the component that we get by looking at the statistical data and providing that prediction, actually try to see if they can do a defect prevention actually. And manufacturing intelligence actually is the main part of using data in a factory. And then when we say data, doing a deep analysis of those data. And machine learning is one of those techniques which it looks at the pattern when you collect data to provide maybe preventive maintenance, or maybe provide like the customer behavior so we can change a product or something like that, which when I talk about the case study, I'll go with more details on any of these. So before I go to the case study, I want to just briefly talk about something we call it the adoption curve when it comes to technology. And this is a good thing for you to learn. You never know, maybe in future you work in a manufacturing company, or maybe you already working in one, or maybe you have your own startup or plan to start a startup. And always there is this question, when there is a new technology, when should I adopt the technology? Okay, so understanding this curve maybe help. I'll slowly walk you through this curve. So this like half S curve, let's say, has 3 phases. And on the x-axis, it shows the different stages of, let's say, time-wise, the progress in terms of the performance. And on the y-axis, you see the relative performance, actually. So suppose a new technology started at time 0 and became mature at this asterisk point. Let's suppose you are at this asterisk point, which you see this new technology is available, is mature, and you adopt it for your manufacturing. So phase 1 is a very fast growth. If you see my cursor here, it's a fast growth. That's the first step. And after that, the growth still continues, but it's not as fast as the first phase. And then you are at this top point when the technology is very mature, and then slowly there are maybe new technologies available, or is not that attractive, and the growth is going to decline actually. So this is for most of the technologies, we can use this curve actually. Now the question is, let's say I adopt a technology and I'm working and manufacturing and building something, and then a new technology comes to the market. When is a good time to switch from the current technology to the new technology? So for that, we're going to look at this curve. Again, take a moment to take at the curve. And this is actually one of those interesting curves that later you can pause and analyze it with more details, because it gives you some good insight. Suppose the first one, the first curve on the left, that's the technology generation, let's say 1, and the second one is the technology generation 2. I explained already the technology generation 1. We start using it, we adopted it, we are happy, fast growth, and then there is this decline coming to end. So, and then the technology 2 started, and there are some overlaps. Of course, I showed the graph like that, but let's say it's earlier on the time. And we can either start it at this pink point, which we on the image it says premature adoption. We may have started it later on this greenish point when the curve inflect here. which is called the ideal tipping points, or we may start at this top point when we realize the technology is declining and it's not that attractive, so we switch to generation 2. So we can start at these 3 points again. We can start at this premature adoption point over here, if you see my cursor, or you can start at the second point, ideal tipping point, is greenish. So if you look at this horizontal line, the first point, the premature point, is that point over here, the pink one, and then the green one is the ideal, and then the top point, which I'll call it the late adoption of the technology. So with each of them, there are some risk and some values. If you start adopting a technology late, of course, it's low risk because people have tried it before, but obviously there is low value for you as well. If you start early, there is higher risk. Maybe the technology is not going to be working, you don't know. But if it works, there will be a higher values. So of course there are risks with an advantage with each of them. With the late adoption, you may start when the new technology is already declining and deteriorating, or your current technologies became obsolete. You cannot stay in the competition, and maybe you miss an opportunity for high value. With the early adoption, beside the risk, but if it works, the initial cost is low because when a technology is new, you can maybe put a small amount of investment to get that new technology. You are at the edge of competition, and also your company, it can brand itself as the industry leader in using a particular technology before everyone else to use it. Okay, now let's compare these 3 scenarios: the people who start at the ideal point, the premature or early adopter, or the late adopter. So the first curve on the left, it shows the ideal point. So you see they started at some point. While they are still using their current technology, they slowly move to the next generation and next generation. The middle one shows the late one. So they started when their current technology has been declined, and now they start a new one. And then the last one on the right, it shows when, as you see, they start premature, so very early. Now, if we put these 3 together, as you can see, the ideal one, which is the first one, they brings like a relatively higher performance compared with the one that they started late. So the late one is even worse than the one that they started premature. So it gives you this idea that there is a higher risk with not starting a new technology. So as you see, even a premature one can get ahead of you if you do not start a new technology or new generation of technology. And of course, there are some general guidance. You can read more about it. I strongly suggest that textbook, again, I'll bring it up here, Smart Manufacturing. If in future, if you work in a company or you're currently working in a company and there is this discussion around Industry 4.0, then maybe reading that book worth spending some time. So, and in general, strategies is we should go incremental, not jumping, and layered. Layered, when we say layered, this picture again explained, is while we are adopting the new technology, we try to continue our older technology and slowly adopt to the new one. So we build on the previous technology or generation, and then we slowly optimize values and lower the risk. All right. I talk a lot about like these general concepts. As I promised, I'm gonna walk you through the case study, which is a sawmill. And sawmills is a big industry in Canada and the US. Lumber manufacturing, of course, is a huge industry. And here in British Columbia, of course, we have many sawmills. And so that's one of old industries, lumber manufacturing. And one of those industries that luckily and they were fast to adopt the Industry 4.0 or Manufacturing 4.0. And I was lucky to be involved in some of these projects, which I'll go through my own personal project, not the entire things. All right, so what is the manufacturing or lumber manufacturing 4.x? Before that, not everybody in the class or if you're listening to it knows sawmill. So briefly, I'll walk you through sawmill. Sawmill or lumber manufacturing, as the name implies, we wish to go from a log to these nice clean lumbers. So previous to getting to these logs is the forestry and harvesting. That's a different story. We suppose that we have a sawmill and we manufacture lumbers. It means our input is the logs, our output are these lumbers. And we have our own customers, of course, which they are the construction builders for homes and bridges and so on. It takes 100+ years for a tree to grow, and we cannot waste it. When we get a log that we have been waiting for 100 years for a tree to grow, we want to get the most out of it. We want to optimize like a little piece, every piece of these precious material, actually natural material. So there are 8 steps, which I'll briefly walk you through that. I'm not going to go to the details. Step 1 is the scanning. A log will scan by X-ray. So suppose there is this X-ray source, and then there is panel. Similar to the X-ray technology in a hospital, it provides you the details about the shape of the log and also the feature inside the log, if there is any cracks or any knots or any shape inside. Here is the actual machine, which I compare it with a hospital X-ray CT scan. You can see the similarity, of course, for the hospital. They can use the X-ray to see if there is any bone cracks or any issues in the body, which is not an area that I know too much. But for a log, the technology is the same. Of course, the X-ray source and energy, the energy is different. We adjust it for a log, but that's the same sort of technology. So that's a step 1, scanning the log. Step number 2 is after you know what's going on with your log, the logs come, of course, with barks. You need to remove the barks, and it's a process which is done in a machine which is called a debarker. Debarker, if you can see through this video, is an automated machine, and there are tools. The log rotates, or sometimes the tool rotates, and it removes the bark actually from the log. So the process can sometimes have issues if, let's say, the blades are dull, or perhaps there are some issues with adjusting the pressure because you apply pressure to the log. If it's not optimized, you may not get the clean, actually, log as you wish. So it requires monitoring. So keep that in mind for now. That was step number 2. Step number 3 is we need to rotate our logs based on the shape that it has to the optimized position. We need to scan it again, if you can see through this simulation. And then we turn our log, which it has a circular, roughly round cross section, to a rectangular cross section. As you see in this video, we turn the log to a cant. A cant is that log, now that you can see it on the conveyor, which has a rectangular cross section. And this is from an actual sawmill. So it used the GeoScan. I'm not advertising the GeoScan company. It's a company in Vancouver, US, Vancouver, Washington, actually, our neighbor. They just put their video on YouTube, so I could access their video. So it shows the scanning technology that they use, and similar to the animation that you saw, you see it goes back and forth to actually turn the log to a nice and clean rectangular cross-section cant. And the whole process is of course, is automated. So here is a different machine to create the cant. It's called the twin bandsaws, and there are like bandsaws on the side. And if you take a close look at actually the machine, you see the whole process is automated. So there is no operators actually controlling that. And it means in order to for this machine to work properly, we need to carefully measure the log ahead of time. So we adjust the distance, or we ask the machine to adjust it automatically, actually. And then, by the way, I'll put the link for each of these videos, which I got it from the Wood Products Expo website, and you can read and rewatch these with more details. And a different machine, which a little bit more complicated, and it's again doing the cant, or making the square shape for the logs. Now we have the cant, we need to saw it to the lumber size that we want. Here is the sawing process, as this animation shows. We have several saws, which we call them saw gangs, and they move back and forth. The distance between them will be adjusted, and they create the lumbers of different size, depends on the cant that we have. Here is an actual sawmill. Hopefully I can play. A part of the process that we saw in the animations, pretty similar to that. You can see the level of automation. If you're interested later, I can provide you more details that have a lot of experience with. You're interested in this industry. But for now, for the purpose of this discussion, I just briefly go through each step. And don't forget, we are still at the manufacturing 3.0, like what I'm showing to you, is the automation part. All right. So to briefly give you an idea, so again, I'm sure majority of you know, so the first industrial revolution was with the invention of steam power, and the second industrial revolution, the mass production, and the third one was the automation, which, as we observe it in the sawmill. All right, so we haven't yet started talking about Industry 4.0. So just providing details that what is this industry currently. Edging and trimming is step number 5. Sometimes the lumbers we created, we need to remove the edges. And step number 6, which is the most expensive step, it requires a lot of energy. And if somebody is smart, can come up with a better solution, and then they would be the hero, and perhaps, or most likely, very rich, is the drying. Remember, wood is a green material. It has a lot of moisture in it. We need to reduce the amount of moisture like by 80%. So then we get not to zero. We don't want a dry wood. We want a lumber which its moisture is in a range that we can use it in many applications. And the woods go through an oven. There is heat and pressure, and then the rest of the story. And it takes 2 or 3 days, and after that, they slowly comes out, as you see in this video. And lastly, after we dry the lumbers, we need to clean and smooth the surface on a planer machine. And we produce our lumbers. Now we need to sort them. For sorting, I mean based on the size, based on the type of the wood. Remember, the logs coming to a sawmills, they are a mix sometimes. There are different species. There might be oak or maybe different types of wood, and they need to be sorted out. They need to be graded, and also based on their size. And this is the sorting process. All right. So hopefully I gave you an idea how lumbers is being manufactured. Um, and you can rewatch, of course, the video later, but there were 8 steps. We started from scanning and then rotating and making a cant. And then we create the lumbers, we trim them, we dry them, and after that we plane them, make them nice and clean lumbers. Now, during this process, you saw there were a lot of automations. There is a chance that something goes wrong, and we want to prevent that. And by prevention, I mean, can we improve the performance? I'm going to focus on one things which I've been involved in this process, and that's the sawing. What about sawing? So here I have an experimental test, hopefully if I can play it, which shows sometimes things can go wrong with our saw. Maybe it's dull or maybe it's getting hot. And then the result would be these wavy lumbers, which they are not acceptable, of course, and we waste a lot of wood here because either we need to resize it by trim it again, it means extra work, or maybe we can like sell it with a lower price, but with this wavy cut as you see it here is not the right size. So just for those who don't know the sawing process, this is an actual sawing test that I did at FD Innovation prior to that. So you see there is a lot of wobbly things happening in the saw because the speed was not right. All right, that was for those who haven't seen a sawing in action. It was, of course, in the lab in a sawmill. Instead of, as you saw in the animation, instead of one saw blades, there are several saw blades. The speed is higher. And if you ever had a chance to visit a sawmill, or maybe you work in a sawmill, I don't know, but it's one of those very interesting manufacturing facilities, which you see all these automation and all these fast-pacing productions. All right, let's focus on the saw machine and see how Industry 4.0 or digitalization can benefit from it, or what do we mean by that. So inside the saw, this is just one picture with 4 saw blades. It's a trimmer machine, actually, if you again remember from the earlier slides. I just showed here the schematic of one saws to show you the setup. If I remove the lumber, then you see the saw itself. There are a pair of guides here which they constrain the motion of the saw. And then I remove the guide, I remove the saw, and this is actually the guide, and you see the main shaft. So here is then the setup, how we assemble them, all right, and how it goes. So one thing that one of those past work that I've done when I used to work at F Innovation, which I'm proud, was the invention of a temperature sensor. Actually, we a group of engineers, we came up with the idea that how we can accurately measure the temperature of the saw. And now it became a product. It's called the temperature sensor, and a company named Williams and White in Vancouver, they are producing these sensors. And many sawmills actually, they buy or rent this tool and they use it in their sawmills. And what it gives you, I don't want you to go through this complex graph. It's just to give you an idea what sort of information it shows you. So on this graph, X is the time and Y is the temperature. So blue is when there is no cutting, red is when the cut happenings, and then green allowing the saw to cool off. So, and if the sensor continuously measure the temperature of the saw, it send it to a computer or send it to your smartphone. So constantly, as the operator of the machine, you can measure the temperature of the saw. But we automate this and we said, okay, can I use this temperature data using some sort of machine learning algorithm to provide any insight into any pattern? For example, if the trend in temperature of the saw is sort of showing that maybe the temperature is going up, so maybe there are some issues, maybe the saw is getting dull, and maybe there are some rubbing against the wood, maybe there is excessive vibration, or maybe the cooling that we are using is not enough. Or sometimes maybe if the temperature is too low, it means we are using excessive amount of water, so our process is not optimized. So this sensor provides this information. The good things is the company is willing to, just to give you an idea, to give you the sensor for free in exchange for the data that you get every day. The reason is you can use those data and provide useful information to the sawmill and then ask for the money when there is an issue. Say, hey, I know there is an issue in your machine because I can see it from the temperature data. Give me this amount of money so I can fix it for you. Just to give you an idea. So, and the next thing is using this advanced machine learning. Again, in academia, we talk a lot about machine learning. In real life, when we talk about machine learning and AI, of course, our mind typically goes to the face recognition, all these advanced digital things, and sometimes we may not think like a sawmill, like a traditional lumber manufacturing can benefit from machine learning. Let's break it down. What is actually machine learning? Because people tend to use the term AI, which is different than machine learning, by the way. AI, artificial intelligence, is using machine learning as one of the tools. And of course, AI use many other tools to get a task done similar to how a human brain works. But machine learning is sort of, you can think about, is a statistical tool, actually. And we have courses here, of course, in machine learning, and I'm sure you know. But in an essence is that adding some sensors to a machine to collect data. It can be a temperature sensor that I showed you. It can be maybe other sensors to measure a physical quantity. And then we use those data with a specific technique to learn about any pattern or any trend in the data. And we use those trends and patterns to predict the future behavior of the machine. All right, so in simple word, we are giving a power to a machine so the machine can learn from its own experience, right? To provide you with, again, another example, which I was involved myself. So I was asked, how can we make this machine smart, right? This is a dumb machine. This is a saw box. As you can see, it's not clean. How can I add a brain to it? Well, I went out and I asked the machine operators in a sawmill, and I asked a very simple question. How would you tell if your machine is working okay or not? And 99% of the time, this was the answer I got. I can hear it. So, because their ears have been trained over years using the machine. Remember that legacy system that I told you, people with experience in a system. Now, by listening to a machine, if it has an odd sound, they realize that maybe there is something wrong with the machine. Maybe the saw is dull or maybe something is wrong. So I don't have that ear, but I can use a microphone and I can do all sort of fancy analysis with the sound, because sound is a wave, and we know we can look at its frequency and color map frequency. Again, don't focus on this graph too much, but I wanted to show you we can use the frequency analysis or all sort of advanced analysis to look at the pattern from this machine and make the machine smart. So here I provide you with two examples that, again, personally I was involved in these projects. I can provide you with more details. If you are interested, let me know later how this works. There are, of course, many projects going on with Sawmills, and there are many left for you to be smart enough to invest on that, especially for a big industry like Sawmills here in North America, and make it smarter. But my point was to tell you how, like, a traditional industry moves from manufacturing 3.0, the automation, to industrial or manufacturing 4.0, and then growing slowly by working with the data and making the system smart. Thank you very much for listening to this case study. Here I'm going to stop recording, and then we'll focus on our own questions. Let me just, and then your concern regarding the logistic for this course. Okay, let me stop